So here's a quick example, just working through this idea or this type of problem where we're moving from an inclined plane into projectile motion. And so we'll have an object, say, sitting on a frictionless surface. Let's put this at, 20 degrees. And the idea is this thing is going to accelerate down the ramp. It'll get down here, have some velocity, which then it shoots off and becomes a projectile. So it'll follow this type of motion. Let me just sketch it in. So it's going to come down and it would land somewhere, some distance here, away from the where it was launched. So we'll call that X. And basically what we're looking at are two different types of motions. So we have, kind of here, we'll call it part 1, and that's just an inclined plane problem. And then we go to part 2, and that's our projectile motion, horizontal velocity. And the transition between those is right here. And so it's basically this velocity that we need to determine. So we'll get the velocity here, and then we move over to projectile motion and use that velocity to figure out how far away it's going to land. So I'm going to break out this first piece, just the inclined plane part. So if we have an inclined plane like this, and we have an object, okay, so we have some angle, in this case 20 degrees. First thing you do is draw a force diagram. So that would be the force of gravity. And then we draw our vector components. So this would be Fg in the y, and then Fg in the x. And theta goes up here. And so it's this piece right here that's accelerating it. We need to get velocity, so we got to figure out the acceleration first. So this is all just part 1. So the first thing, determine the acceleration. Normally we would say x, but I'm actually, since this is x in this way, I'm going to call this r. So we're going to call it like y, or not even y, but we'll just call it r, the r direction, because it's not really in the x. It doesn't matter. You could use x. Just know that this x is different from this x. Okay, so we want to find the acceleration down the ramp. So the acceleration down the ramp is going to be the net force down the ramp divided by the mass. And so what we get is the only force acting on it is this force of gravity in the x, which is the force of gravity sine theta. So sine 20 divided by the mass. So we get the acceleration down the ramp is going to be mg sine 20 divided by the mass. Substituting in values, the m's cancel. So we get 9.8 times sine 20. And let me calculate that. So that results in an acceleration of 3.35 meters per second squared. Note that I rounded here. So we just introduced some error, but I'm just going to go ahead and carry on with the calculation. So now that we know the acceleration of the object, we go to part 2, which is determine the final velocity. Okay, so we don't know the time that it's going to spend, but we do know the distance that it's going to travel. And I'm going to call that r. That's bad. So it goes some distance down the ramp. So we use the acceleration that we just did, and we don't know time, so we're going to have to use Vf squared is V naught squared plus 2a times, instead of x, I'm going to do r minus r naught. But it's just that's the change in r. Okay, so let's suppose that it goes, 2 meters. Then we would just plug in our values. So my final velocity squared is going to be 2 times the acceleration, 3.35, times the distance it traveled, which was 2. And then to get rid of the square, we take the square root of that. So my final velocity for the ramp is going to be 3.66 meters per second. Okay, so now we're done with part one. So this was all just the first part, the inclined plane part. So this thing came down the ramp and it leaves right here with a velocity of 3.66 meters per second. And that came from this first part. Now we're going to move to the second part. So this is all just part one. So now part two. Part two is just this projectile. So we need to know this height. So let's suppose that the height is like, I don't know, 1.2 meters. Okay, so now it's projectile motion. So since I know the height, we're going to work in the y direction. And in the y direction, the acceleration in the y is equal to g. And what we want to know is the time it's going to take to hit the ground in the y. So we have y naught plus by naught t plus 1/2 ay t squared. The initial position, 0, the initial velocity in the y direction, this is all in the x, so that's 0. So we get y equals 1/2 the acceleration in the y. Oh, I'm sorry, let's go ahead and change that, because we know that that value is g times t squared. The y is 1.2, so we get 1.2 equals 1/2 g t squared. So we multiply that by 2, so we get 2 times 1.2, and then divide by g, and that's t squared. So I just multiplied the 2 over and divided by g. Now to get rid of the square, we take the square root. So the time in this case is going to be 0.49 seconds. The time now, so now we know the time it takes to hit. Now we just figure out how far it goes. That's in the x direction. In the x direction, we know the acceleration in the x is 0. Draw a line to separate these. So again, we go to our position function. And we can cancel some stuff out. The initial position will be 0. The acceleration in the x is 0. So we get the position is going to be the velocity in the x direction times the time. The velocity in the x is what we found previously. It's the velocity coming off the inclined plane. So we get that the position, the displacement, where it's going to land, is going to be the 3.66. All that velocity is in the x direction times the time, 0.49. So we get 3.66 times 0.49, 1.79 meters. End of problem. So this thing is going to land 1.79 meters away. And that's part 2. So this problem, break it down into 2 parts. Each one has 2 parts. So you figure out the acceleration on the ramp to get the final velocity. Then the velocity we use over in projectile motion. Figure out the time it takes to hit the floor, and then we apply that in the x direction to find the distance traveled. So that's the Hot Wheels problem, but it's a typical type of problem that will come up.